In Chapter 10, we're going to be looking at some further applications of our trick. Now in Section 1 and 2, we're going to take a different approach and we're going to be working with non-right triangles. Up until this point, everything we've done has always been a right angle, which has given us different information and allowed us to manipulate things as we need them. So in this section, we're going to start with some non-right triangles and we're going to be working with the law of sines, which we'll see this in a minute. Before we get going, we do need to kind of look at some vocabulary and some triangles and talk about some things before we kind of dive into these non-right triangles. So the first definition I'm going to look at is altitude. Altitude is defined as a perpendicular line from one vertex to the opposite side, forming two right triangles. You might also think back to your geometry days when you're looking for the height of a triangle. This would also have been your altitude. This will be beneficial to us, as if we can form right angles, then we can go back to concepts we already know. Number two, we can look at the term oblique triangle. This is known as a triangle that is not a right triangle. So you're either oblique or you're right. And that's your two options. Then we're going to get into some more stuff that you might remember from your geometry days, such as ASA. It stands for angle, side, angle. I'm talking about the information that is given within our triangle. And so this would be an example of an angle, side, angle triangle that we have here. Things that we know about it. We know this angle, we know this angle, and we know this side. Based off the information that we're given, we'll be able to make some assumptions and move forward with the problem. But I just want to kind of go over some of these abbreviations and what the triangle may look like. There's just one example here. The next one is AAS, which is your angle, angle, side. So if I know this angle and a side, you can notice this side is outside of the two angles where this one was in between. Then I'm looking at an angle, angle, side situation. And then side, side, angle. Notice I have a side, and an angle. And this one actually leads us down a path of kind of a lot of unknowns because we know two sides, but we know the angle outside of it. So we don't know what is this one. Is it right? Is it acute? Is it obtuse? We're not real sure. And this leads us into the last one of something known as the ambiguous case, which we will work with as we move forward, and it is where more than one triangle may satisfy the criteria. And so this side angle triangle is going to kind of get us into a mess because we don't know enough information about it. We can make assumptions and create multiple triangles that meet the just basic given criteria. And so we'll begin to talk about this ambiguous case as we move forward with this. So I just wanted to kind of start with some vocabulary, talk about it, before we move into this next one and looking at part B here, the law of sines. Now the law of sines, if you check into your text, there's a proof on how we get to this, but it says that given a triangle with angles and opposite sides labeled as in the figure, so let me draw this figure for you. Say we had some triangle here. They like to label the sides A, B, and C as in lowercase a, b, and c. And then they like to label the angles using Greek letters, and they always make this relationship. Across from side A, we'll have angle alpha. Across from side C, we have gamma. And across from side B, we have beta. And so they always make this triangle. And so it's important for you to understand where angles and sides go within this triangle, because sometimes they're not going to give you a picture. So you need to draw some sort of picture to kind of get you going. So this is the figure they're referencing here. And they say that the ratio of the measurement of an angle to the length of its opposite side will be equal to the other two ratios of angle measure to opposite sides. So there's a ratio relationship between these sides and these angles, and we can use that using the law of sines, and it's based off proportions. So if you go back to what you were doing back in algebra days and solving a proportion where you would kind of cross multiply and solve it out from there, that's what we're going to use here to help us to solve things out. So this law of sines, you don't have to have all three ratios. You just need one ratio where you know your numerator and your denominator, and another ratio where you at least know a little bit of information about it. Either you know a side or an angle, and you can work it from there. It's not important to memorize this top one and this bottom one. They're just showing you numerators, denominators don't matter as long as your proportions are all set up the same. Again, going back to what you know about setting up proportions and solving them. And so we're going to use this law of sines as we move forward in section 1, but as we move forward in the chapter, we cannot forget about this. We are going to use this in other sections to kind of pair up with stuff for our end game of being able to find out any missing side or angle of a given triangle. So let's look at this example here. And this it says, solving for two unknown sides and the angle of an angle-side triangle. Solve the triangle to the nearest tenth. And so what we want to do is we want to find all the missing sides and all the missing angles. So the first thing I'm going to do is I'm going to find the missing angle here. So kind of my first step is I want to find the missing angle. I've got two angles. We know that a triangle in and of itself, whether oblique or right, has a total of 180 degrees within that triangle. So since I already know two of them, my goal is I want to find side B, side C, and this angle beta. Okay, those are the three pieces of information that I do not know. And so the first thing I'm going to do is I'm going to find angle beta. I'm going to take 180 degrees, I'm going to subtract off 50 degrees, I'm going to subtract off 30 degrees. Doing all of the subtraction helps me find angle beta, which is equal to 100 degrees. And so I can just label it here so I can visually see what's going on. But if you like, I can make a little chart here. We know that alpha is equal to 50 degrees, beta we know is equal to 100 degrees, and gamma we know is equal to 30 degrees. So in relation of solving the entire triangle, I know all the angles now. Now, next step that I want to do is I want to start working with these sides. Now, this is not a right triangle, so I'm not going to pull out Pythagorean theorem by any means in trying to find the different stuff, but I do want to use this law of sines. You'll notice that in relation to sides and angles, because in law of sines I've got to have that relationship, I know this relationship here. I know that sine of alpha over A would be equal to sine of 50 degrees over 10. And so I'm going to use that as kind of my basic ratio to get me going because they told me it was 50 degrees. They told me this one is 10. So I at least know that relationship is a given and I haven't messed up anything. The next thing I'm going to do is I'm going to set up another ratio to go with this. So I'm going to have sine of an angle over a side. And with this one, it doesn't matter which one I start with. Say I want to start with this 30 degrees. So I'm going to say 30 degrees here. It's opposite side C, so side C is here. And then I have a proportion I can solve. So I'm going to cross multiply. So this gives me 10 sine of 30 degrees equal to C sine of 50 degrees. And now it's just a matter of solving for C. So I'm going to divide both sides by sine of 50 degrees. Now you do need your calculator handy. Notice we are working in degrees in this, so I need to go in my calculator. I need to make sure it's in degrees before I start working with these trig functions. In this section, we're going to work a lot with degrees. Later on in this chapter, we're going to move back to radians. So you need to be able to toggle between those two functions. So in your calculator, you want to enter 10 times sine of 30 degrees. I would go ahead and hit enter, and then do that answer divided by sine of 50. And it said round to the nearest tenth, and so this gives me 6.5 for my C value. So up here, I now have the value of 6.5 for C. So if you like, I can make a little list here out to the side to see what I'm missing and what I know. I know A is going to be equal to 10. C is 6.5. So the only thing I'm missing in this triangle is this angle B. Now I can use this relationship of sine 30 over 6.5 to get this out, but I always like to go back to my givens, my knowns, just in case I mess something up. Like in case I messed up something in computation here, I don't also mess up another answer. Also, 6.5 is a rounded answer for me. I round to the nearest tenth. And so I'm going to use this 50 and 10 again so that I know I'm not also using a rounded number. So I'm going to use sine of 50 degrees over 10, and I'm going to set it equal to, now I'm going to work in order to find B. So I'm going to say sine of 100 degrees over B. I'm going to follow the same pattern that I did in part 2 here. I'm going to cross multiply in order to solve this out. So this gives me 10 sine of 100 degrees is equal to B sine of 50 degrees. I'm going to solve that for B, so I'm going to divide both sides by sine 50. And again, I need to make sure my calculator is in degrees. Go slow, 10 sine 100 degrees, hit enter, divide it by sine of 50, hit enter, and this gives me a value of B equal to, round it to the nearest tenth, 12.9. And so you can see that I didn't use Pythagorean theorem. I didn't use stuff that I already knew. I'm using this new law of sines to help me to complete this triangle. So let's look at here, number 2. It says using the law of sines to solve side-side angle triangles. Now here's where we were looking at the vocabulary. I told you we were going to learn about some ambiguous cases. So what happens is, because we have two sides and an angle that's not contained by them, we're unsure of how those two sides are relating because we don't know the angle within it. So what happens is, if our side A is less than our height, then we might end up with no triangle, meaning those two sides might not come together. If I get a situation where my side A is equal to the height of my triangle, I end up with a right triangle. No big deal there. If I notice that my side A is bigger than the height and less than B, I'm going to end up with a possibility of two triangles. Is this A side coming down like this, creating an acute angle, or is it coming out like this, creating a slightly obtuse angle? We're unsure of its placement because of its length. Or if we know A to be greater than or equal to B, then we end up with only one triangle. So figuring out if you have one triangle or two triangles is all going to be dependent on what criteria you are given and what you know in relation to your trig identities, etc. So in this one, we're going to solve an oblique side-side angle triangle, and we're going to solve the triangle for the missing side and find the missing angle measures to the nearest tenth. So the first thing I want to do is I want to look at, what do I know? I know that this is equal to 6, and we'll call this one A because it's opposite of my alpha. I know this one's equal to 8. We're going to call this one B because it's opposite of my beta. And then we're going to see what we can figure out in relation to these angles. I need to figure out this angle, and I need to figure out this angle, and then I'm going to have to figure out my missing side here. Okay, so the first thing I'm going to do is I'm going to set up a law of sines ratio, and I know that this is the only angle I know, and I know the side opposite of it, so that's going to be kind of my base proportion that I'm going to work at. So I'm going to say sine of 35 degrees over 6 is equal to, and let's do sine of beta to get us going. Let's find this angle because we already know its side. And so I'm going to say sine of beta over 8. And so I'm going to cross multiply like we did in the previous example. So this gives me 8 sine of 35 degrees equal to 6 sine of beta. So in this one, I'm going to divide both sides by 6. And so I get 8 sine of 35 degrees. Again, make sure you're in degrees. Hit enter. Divide it by 6. And you should get about 0.6765. And that's going to be equal to my sine beta. Now, in order to solve for beta, I'm going to have to use arc sine. So I would get beta equal to arc sine of 0.765. Now, you already entered this and should have this answer sitting in your calculator. And so what you want to do is use that answer and do arc sine of this answer to give you the angle measure of 49.9. Now that I know what beta is, we need to consider what's going on. Is this beta really 49.9? Well, consider this. If you go back to your unit circle, remember it exists on your coordinate plane, and the y value is sine. So if I look at this, I have attained the angle of 49.9. But you'll also notice having a sine value of 49.9, that's my y value. It's also possible that it could have existed over here because my values are positive. Y is also positive in quadrant 2. Because of the arc nature, it only found values between negative pi over 2 and pi over 2. So this one could have also existed over here. So if I were to go up 49.9, this entire angle here is actually 130.1. So I have to consider, which angle is this? Is this angle 49.9 or is this angle 130.1? Well, actually, we are going to use the angle 130.1. You'll notice that if I were to extend 6 out here to the side, because I don't know this angle, this would also be 6. I could extend this triangle here, and so here's where that 49.9 is coming into play. We can clearly see that this is an obtuse angle, and we want to take the obtuse from it.